Hi everyone. Welcome to our next episode on energy. That's what we'll be doing today. This will probably be our longest episode so far. Well, let's get started. So, when we did forces, right? Understand the diagrams. It's not really the equations that are important, it's the diagrams. I showed you the three laws of Newton. The first one is the sum of the force is equal to 0, where the force isn't moving, but we argued and said it moved. It's just that it moved in equal and opposite directions. And then we said the sum of the force, the force was equal to mass times acceleration when the object was in motion. And then we talked about equal and opposite reactions. So if you remember carefully, the first diagram we had was when we talked about a vector. When we talked about force, we were inferring to a vector, right? This is not a good sketch. So imagine you're going to have a sphere, right? And then if a vector is going this direction, which has to be force 1, right? It's going towards the sphere. Velocity is constant. Which is coming out. And then on the other side, we said that F2, force 2 is equal to negative force 1. Whenever there's a force, there's an equal and opposite force. Okay, that was one of our diagrams. And then when we talked about some other sphere, right? When it was pointing downward, the gravitation was going. Acceleration due to gravity is at g, which is a vector. Let me do a better drawing of this. So when the sphere was coming down, right? Acceleration due to gravity was also going down with this, right? And then what was coming down, we said that the weight... Sorry, I apologize about this. When we said it was coming down, right? On the side we said weight is equal to mg, where g... Acceleration due to gravity is a vector and mass is a scalar. And then acceleration due to gravity was coming downward with the gravitational field. Well, this is the weight field. Okay. And then we talked about one more last diagram is about the sphere. When something was pointing out of the sphere, which we said this is force 1. Well, you call this force 1 on 2. And then it gives us an opposite force 2 on 1. Wherever there's a force is an equal and opposite force. This third one acts the same as this one. And then I think the equation for the first one is you would have to say force is equal to 0, but we say the sum of the force has to be, this is not a good equation. Instead of saying the force, we say the sum of the force is equal to 0. The second one would follow the concept of the sum of the force is equal to mass times acceleration. And then here we'd say that the force 1 on 2 is equal to negative force 2 on 1. Right? This is our first sphere, our second sphere, our third sphere, and then the equation that goes with the first one is this equation. Equation that goes to the second diagram is this equation. And then the equation that goes to the third diagram is this equation. All right, it's you could see how much better this is, because with kinematic equations, we had to worry about 4 equations. Newton's laws, we only have to worry about 3. Okay. Now, I'd like to just start with forces before we get into energy, because it's a very interesting way to understand energy, because force is a vector. You're going to find out what energy is. Energy, believe it or not, is a scalar, just like time. But we'll get to that soon. So when we talked about forces in the last video, I did not mention internal forces. I didn't talk about internal or external forces, because there are none. When you do forces with Newton's laws, there's just forces. We don't have to worry about internal or external. What we worry about are conservative and non-conservative forces. So anything that's conservative, like a conservative force, would be like gravity would be a conservative force, acceleration due to gravity. Non-conservative would be like friction. Like if you had static friction, kinetic friction, friction that's not moving, friction that moves, we call them non-conservative forces. They, non-conservative tends to turn into heat. It gives off some kind of dissipated heat, which is produced off in the universe, and we never get it back. Conservative is more of what we can use, like if we have like power, for instance, is conservative, because we can get it back. So anything conservative, we'll get to that when we talk about energy, but anything we can get non-conservative forces, the forces get lost in the system forever. And they're kind of a pain in the butt, because they kind of just pop up. But without static friction, light bulbs would not like stay in sockets and things like that. You got to just keep in mind about that too. So Edison's things with light bulbs would not even work, and Tesla, believe it or not, invented the light bulb. As much as I want to say this, because Nikola Tesla, he made 80% of the bulb, but we'll save all that stuff when we get into electromagnetism. But if you want to really talk about the bulb, the only thing that Edison came up with was the filament, but Tesla came up with the whole base of the bulb. So Edison did not really invent the light bulb. He only invented 10% of the light bulb, maybe 20% of the light bulb. I would say 20%. Tesla invented 80%. I don't know why he's not credited, because he invented the light bulb. He really impacted electricity in an 80% capacity. Now, we'll save that for when we get into season 2. I'm not going to worry about Tesla or any of these people. They have nothing to do with what we're talking about. Okay. So what I'm trying to show you this is, imagine that there's some kind of a planet, like a sphere, right? And something has to act on it, and then something has to act out. Now, there is a couple of pages I want to show you on another book that I have, because it is less than 10% of the material. This is a book that I don't know if it's possible, but it still hasn't been solved. I was told that it's not real, but it's called Hollow Planets by Jean Leprecht. And what's funny is, I have the same middle name, it's Jan. Other than that, it's a very interesting book. As you can see, it's like a planet, and then there's another planet inside of it that has a center sun. Like, it's got its own light source, per se. A hollow planet is a planet that can contain its own power, like its own solar power and solar energy. So it has its own sun in the center, and it's kind of just shielded off. It's interesting theory. The Earth is hollow. It's just that it's not habitable. How should I say the word? Habitably hollow, if that's a word, habitably, but it's not habitable hollow. Like, it's uninhabitable. So it is hollow. It's just that it's not for a living environment. I'm sure scientists would agree with that notion. The planet is hollow. It's just it's not habitable, because it has too much it has too much extreme temperatures and not enough sunlight. Venus, for instance, is like one of those planets, if you could think about it. It is my astrological ruling planet, which is the planet of balance and peace and all that. All right, I'm going to show you something really interesting. Now, I want to show you an Euler impression on forces. Like, we're going to go past Sir Isaac Newton. I mean, we talked about him at the very end of 2D kinematic. Well, actually, we talked about him at the very end of 1D kinematic equations, which was the first episode. And we talk about him in forces, but now we're past Isaac Newton. I want to show you an Euler impression on forces, which is very interesting. Now, Leonhard Euler was a Swiss mathematician. Was not a physicist, he was a mathematician. And I'm more like a mathematician than a physicist, but I love physics, so you can't be a good physicist if you're not a mathematician. So, okay, let me talk about Leonhard Euler. So Leonhard Euler was born in 1707 and died in 1783. And there's something I want to show you very impressive about his work. I can find it. So this is like Newtonian gravity revisited, basically, is what I'm showing you. So you're going to have net movement, forces, masses together. So Euler imagined that with forces in the universe, if you're in space between planets and things like that, they had what was called a pressure. He believed that gravity was a pressure because it had to flow through planets. He actually thought it was a pressure because he said a pressure has to have some kind of ether, right? And even though space is not an ether, I mean, it has no vessel to contain a pressure. He said something about a pressure because it can flux around planets. It's in this book called Hollow Planets, but he believed it was a pressure. That's what his interpretation of gravity. And he believed in all these tensor vectors. So each vector coming out is showing you the pressure that's pulling the object away, and then a pressure coming in. In space, we call these Lagrangian points. So they kind of show you that these relate into today's world of Lagrangian points, but these are pressures. It's kind of like acupuncture, where when you have a nerve ending, right? And you have a patient who has some kind of illness and they need some kind of rehabilitation, you could say. Because acupuncture is the most effective way to sober an alcoholic. I mean, it's the most effective medicine there is. It's foolproof. So imagine that you take a patient to the acupuncturist, right? Now they're going to apply some pressure. They're not just going to put needles into you. They're going to do some pressurization. So what they do is they kind of they have to constrict the muscles, and they have to squeeze and everything and hold the tissue and align it again. I mean, that is the idea with an acupuncturist. And then they have to put needles in to keep the nerve endings intact. Well, biological application of what I'm trying to show you here. So these are pressure. These are pressured, like, tensor vectors, I guess you could call them, tensor vectors. But basically, these vectors are keeping these planets in one spot. So, like, basically, when there is what's going on with this diagram, and then the same thing is happening on this next page. So let me show you exactly what this is saying. When we have an object in space, right, we say sum of the force is equal to 0. Euler imagined that there had to have been something pushing onto that object to keep it fixed. So imagine if something was pushing it this direction, right? The object is going to freely want to move this direction. But then let's say if it's being pushed this direction, then the object is freely to go up and down. But then let's say it's fixed up, and then it can only go up, right? And then it's fixed this way, now it's stuck. And we just keep adding more and more unit vectors, right? Or tensor vectors or vectors. They're just words. We keep adding more and more vectors until we can't get the object to move. I mean, this is a very interesting way of understanding energy. So imagine that we can't move the object because it's being tethered in every direction. That was Euler's idea. And he said something about a pressure, and I can't remember how exactly on this video, but I think he said because if it had to have some kind of, I remember now. He said if it had to have some kind of flux, which is fluidity. Now, flux is Greek for flow. It does not mean flux capacitor from Back to the Future. The word flux means flow. He said only pressure can have a flux. But this is the idea of the sum of the forces equal to 0. Now, the second one is very simple. So if I push an object this direction, right, it's going to want to go this way. That's the second one. The third one is just saying that if I push the object, if I pull on the object, I could possibly get an opposite reaction. It's almost the same thing, right? Let's reinterpret this. So I can imagine that I'm pushing on it, and then something else is pushing back, and then it's going to come twice as far. It's kind of deep, but imagine that there's some kind of wall, and it's like stopping the sphere, and it comes right back. Okay. It could be a hypersphere. Let's imagine this thing has, like, I don't know, 4 dimensions or more. So I just wanted to show you about this pressure idea. Other than that, this is the only thing you're going to see with vectors. I do have to show you vectors, but it's not, we're going to learn vector multiplication. Okay, so when I showed you vectors, right, when we did chapter 2, that was vectors. Chapter 2 was heavy on them. And so, well, 2D kinematic equations was heavy with vectors. And then 3D relative velocity, I had to show you vectors. Forces, we did vectors, and I have to show you vectors again. So we only really came across, well, we did unit vectors. You don't really need to worry about those. Those are more for season 2, and you're going to see why we use unit vectors, why they're more needed in season 2. We don't need them in season 1. So unit vectors, if I want to add in the linear world, all right, we're not just in the vector world, we're in the linear algebra world, we're in the linear world. I cannot subtract in the linear world. In order to subtract, I must add. It's a rule. Division does not exist. If I divide, I have to multiply by a fraction. If I subtract, I must add with a negative. So in the linear world, you cannot take something minus something. You have to do, let's say if I have 1, or let's say if I have 5 and I want to subtract 3. We can't, in the linear world, we cannot write this. We cannot use this. This is illegal. We cannot use 5 minus 3 is equal to, in the linear world, we cannot say 5 minus 3 is equal to 2. This is not unacceptable. We cannot use that. And the reason why I want to show you that is because this is how math was formerly understood in the eastern part of the world. So if I want to reinterpret this, 5 minus 3 is equal to 2, I have to say 5 plus negative 3 is equal to 2. I must add a negative. That's what they call vector addition. There's no such thing as vector subtraction. Now, it's the same rule with the linear world. I cannot subtract a number. I must add a negative number. And the same thing goes with multiplication. So or division. So let's just say, let's do a perfect number that can divide without a remainder. So let's say if I take 9 over 3 is equal to 3. Because division is really just a fraction. I mean, I can't say 9 divided by 3 is equal to 3. That is unacceptable. In the linear world, I must say 9 times 1/3 is equal to 3. See, what I'm doing is I'm turning division into multiplication, and I'm also turning subtraction into addition. It's the linear world of things. And the thing, too, with the linear world is pretty much multiplication is really non-commutative. Now, what we say with the words commutative, where we could say that 5 times 3 can be equal to 3 times 5. Now, if you're in the nonlinear world, this is true because 5 times 3 is equal to 15. 3 times 5 is equal to 15. But in the linear world, it's nonsense. It does not equal. 5 times 3 cannot equal 3 times 5. The number of rows times the number of columns cannot equal the number of columns times the number of rows in a matrix. That's what the 5 and the 3 stand for. Number of rows, number of columns. So rows is like if you have a matrix and you go down this way, and then columns is if you go from left to right. So this does not work in the linear world. A times B cannot equal B times A. I just thought I'd give you some lessons on linear algebra. It's a strange course, but it's fun. It's interesting. Okay. Don't worry about that. That linear stuff, don't even worry about that. I just wanted to kind of give you a little sneak peek on linear algebra because it is my favorite math subject ever. I mean, I like it as much as I like calculus. Because I honestly think that everything, like, what if we're in the matrix, which I'll save that after we're done with energy. I mean, what if everything is just a linear predetermination? Because whenever you have a linear system, you got prediction made. When anything that's non-linear, you don't know what the end results are going to be. But what if we're just programmed to not know that? But I'll save that when we get into energy discussion. Okay. Alrighty then. I'm going to show you the dot product, which is a scale. Now, in vector multiplication, there are two types, which you also learn in linear algebra. There is the scaling product, which is actually the easiest form of multiplication throughout both linear world and the vector world. See, the vectors act really well in the linear world, in linear algebra, than they do in calculus. They kind of are respected and treasure trove more. I mean, they're kind of like warriors. I mean, you could think of them as like, vectors could be somewhat, I guess they could be interpreted as the shogun, which is like a military in Japan. But in the linear world, they're favored. Linear world loves vectors. Calculus is like, yeah, they're great. We have them. Let's worry about curves, and we'll save them for Calc 3. We'll save them for when we do multivariables. But in the linear world, they're just a treasure trove. Like, they're well honored. I mean, they're well honored veterans. These vectors, they're well honored, and they get their paid respects in the linear world. And you'll see what I'm talking about. And like I said, on this point onward, I'm not really going to show you any calculus. I mean, this is just all linear algebra. I had to show you some calculus before, but I have to show you vectors. I mean, it's a part of calculus, but it's not really a something we need to worry about. So let me pull up vectors again. I have to show you the scaling product. Before I get started, let me do a little quick demo. So with multiplication, you can always use an x, right? You can always do 5 times 3. We're just going to stick with 5 and 3. Or let's change the numbers. Let's do 4 and 4. Now, if I want to multiply two numbers, right, I have two choices of a multiplication symbol. I have the dot, or I have the cross. What's funny is in this standard world of math, this just represents the same thing, but in the vector world, this is a scalar, and this is the cross. This is a vector. They call this the scaling product, and this is called the vector multiplication. This is scaling multiplication and vector multiplication. It actually means something, and I'll show you what that is. But we're not going to do cross. Cross is when we get into rotation. You're not even going to see cross product when we get into linear momentum. Now, what's funny is linear momentum is just like this chapter on energy, but I don't feel like getting involved with it this week. But you're going to see how it's like the vector interpretation of what I'm trying to show you. So, the word scalar, right? I showed you scalar. So far we know that time is a scalar mass is also a scalar, right? We learned how time was a scalar when I showed you 1D kinematic equations, 2D kinematic equations, 3D relative velocity, and I was trying to get into 4D space-time. That showed you that time was a scalar, and then we learned how mass was a scalar a little bit when we got into forces. Okay, so ignore all these little numbers and multiplications, but I'm going to show you what's called the dot product. They call it the dot because it has a dot symbol for multiplication. Okay, so I must show you some definitions first. I don't know what I should show you. Now this is a nice way of understanding math because this is actually a vector cancellation. On episode 1 I said I hate using vectors. This isn't really a vector concept because the vectors are going to cancel out, and you'll see how. Okay, so in vector world, right, which fits better in the linear world, u dot v, right? We use two variables. U dot v is, and this is the commutative property. Well, let me show you this one first. You get u1 v1 plus u2 v2. And that's if you want to know the definition of a dot product. And then if you wanted to do more coordinates, and then you would say that u, on the side you would have to say that u is equal to u1, u2. And then v is equal to v1, v2. And then you would have that. And then if you wanted more variables, like if you wanted to use 3, you just use the same thing. These should be brackets because they're vectors. No parentheses. Okay. Now if I wanted to throw in more variables, it's just the same thing. U is equal to u1, u2, u3, v is equal to v1, v2, v3, and then u dot v is equal to u1, v1, plus u2, v2, plus u3, v3. Okay. And then if you want to know the commutative property, that we would just say, I don't know if I should have to show you all these, but so if it's commutative, you'd have to say that u dot v is equal to v dot u. That's commutative property. And then distributive property is you would say that u dot v plus u is equal to u dot v plus, they use a different variable. Could see that. Okay. U dot v plus w. And I think these all have to be vectors. It's equal to u dot v plus u dot w. Okay. All right. And that's commutative property, and then you're going to have associative property. These are different forms of multiplication. And I'm not a math major, I'm a physics major, so I'm just kind of rolling through these. So C is a scaling value, is C of u dot v is equal to Cu dot v. equals u dot cv. So this is associative. Associative property, distributive property, distributive property, and then commutative. Property. And these are all methods of multiplication. That's what these are. These are methods of multiplication. That's what these are. All three of these are methods of multiplication. There's three different versions. You can have commutative property, which I showed you. Distributive property. Now, distributive property just means we're distributing. So I'm taking the u and I'm distributing the u times the v times the w. It's kind of like foiling. So what they mean by distributing is you're doing this basically. I'm taking the u times v plus w, right? And I'm distributing that. That's distributing property. And then the last one, associative property, is just showing you the, it's kind of the same thing. You're still distributing, as you can see. There's just a multiplication inside instead of an addition. Okay. Now, another interesting perspective on the dot product is it's also the angle between two vectors, but they have to be two non-zero vectors. So the angle, now this is a mathematical definition, it has to be greater than or equal to 0, which is greater than or equal to pi. And basically what they're saying is if I have like a u, right, if I have a u and then I have a v coming this way, and they have to have vectors. I mean, if they're vectors, they gotta have the symbols. The dot product, we can think about it as vector subtraction, which is the same thing as vector addition, v minus u. I just showed you that correspondence. So there is vector subtraction. It does exist. I just didn't feel like explaining it, but it's the tail. It's the angle between. The reason why it's subtraction is it's from tail to tail, the vector. If it's from, and then we call this theta. The angle between the two vectors, we call it theta, and then dot is the origin, I guess, where the origin is centered. So one way of thinking about the dot product is it's the angle between two vectors. I had an argument with a math student, and he told me it's not. It is, because this is the geometric definition of the dot product. There is a course that you could take called college geometry, which I'm planning on taking in a four-year school. But it is the angle between two vectors. That's its geometric interpretation. And since it is, you can say that the cos theta is equal to, I'm going to write it up here so it makes better sense. So we could say that cos theta is equal to u dot v divided by the magnitude of u by the magnitude of v, which this almost acts like, now the double lines mean magnitude. This almost acts like unit vectors because you have the vector over this, but it's two unit vectors that are multiplied from each other. Because remember a unit vector, like let's say if I want to know what's u hat. U hat is just u divided by the magnitude of u. And then the same goes with v hat. So we could say that v hat is also equal to the vector over its magnitude. right? So to clean this up better, I mean, we're trying to find theta, so we say cos theta is equal to u dot v divided by u times v, its magnitude. Now, okay, let's say if we wanted to find the angle, right? We want to find what is this angle. What if we didn't know the angle? Like, let's imagine that we don't know the angle, which we don't know here. How would we actually find the angle? We'd have to take the arc cos. So we'd have to say that theta is equal to the arc cos of this entire thing, this whole thing here. So it'd be the arc cos of u dot v divided by magnitude u times magnitude v. So what's really nice about the dot product is since it's the angle between two vectors, we could find that angle by reinterpreting the arc cosine of this entire thing. Okay, it's just a transcendental function is all it is. It's like this is like taking a logarithm and turning it into an exponential. It's like taking a log to an exponential or a natural log to an exponential. Both natural log and logs are the same thing, and you'll see logs in the next season with Sam. But it's the same interpretation with the trigonometry. So I just thought I would point that out. I think that's awesome. Like that's a nice tool to have. I mean, the fact that we can find the dot product, and there is an alternate form to this equation, by the way. I'm going to turn the page and show you the alternate form. So I could say u dot v is equal to magnitude u times magnitude v cos theta. Okay, this is just a nice little equation. But like I said, this one's really the important one. Well, I wrote it again down here, didn't I? This is the nice one we like. We like this equation because we can find an angle with vectors. I mean, how nice is that? All right. I think that is it. This isn't really going to explain the scaling too much. This is just going to explain the angle between two vectors and also how to do the dot product. All right. In order for me to really show you the scaling process, we are going to have to get into linear algebra. Because there's certain things that work, and there are certain things that won't be enough. Like there's some stuff I can show you it'll work, but it can only take us so far. Okay. I am going to show you some stuff from linear algebra. Now we're going to cover the Gram-Schmidt process. Now this is a chapter called orthogonality. Orthogonality and least squares. Now least squares regression is something you'll find upon taking a course called statistics. I've never taken that course, nor did I need it. Let's find something that's really going to be beneficial, what I'm trying to show you. So I don't think we need orthogonal projection. I think I'm just going to show you the Gram-Schmidt. I might end up actually showing you least squares. Yeah, I'm going to do that too. I'm going to show you least squares. So we are going to do a little bit of, we're going to just touch, we'll get a little intro to statistics. Yeah, I'm going to have to show you a couple of things with this. We're going to pick a problem, don't worry about that. Okay, we got to do the Gram-Schmidt process. The Gram-Schmidt process is a simple algorithm for producing an orthogonal or orthonormal basis for any non-zero subspace of R raised to n. All right, and I have to pick a problem to do as the Gram-Schmidt process. Just trying to figure out. All right, we are going to cover the Gram-Schmidt process. We're gonna pick a problem. Just give me 1 minute. I have to pull it up too. Okay, I don't like this. So we're gonna do the Gram-Schmidt. Just gotta pull this up. Still here. And we gotta do chapter 6. Chapter 6 is orthogonality and least squares. We are in... Okay. Alright, so the numbers we're going to have for the Gram-Schmidt process is 2 sets. Alright, these are going to be matrices, but these are vector form. And I'll show you how they're vector form. We didn't really do vector form in the last episode when I showed you what came in and what came out. I didn't want to show you vector like matrices when we covered. I'll put this here for now. I didn't want to show you matrices when we covered kinematic equations because the math was so tough that it was just too much to show. So because we had to deal with those. You know, they're the hardest part with physics. But now, since we got to forces, I can start showing you matrices. So you have 0, 2, oops, this should be 0, 4, 2. Okay, 0, 4, 2. And then you're going to have 5, 6, negative 7. Okay, so you're going to have 2 sets. Now we have to use the Gram-Schmidt process to produce an orthogonal basis. All right. Okay, so you're going to say that V1 is equal to X1, which is equal to 0, 4, 2. And then you have to say that V2 is equal to X2 minus X2 dot V1 divided by V1 dot V1 times V1. You can think of that as a scaling, which is going to be equal to 5, 6, negative 7 minus 0. It's these numbers, by the way. 0 plus 24. They multiplied this number, so 0 times 5 is 0. 0 plus 6 times 4 is 24. So it's 0 times 5 plus 4 times 6 plus 2 times negative 7. This is following the dot product. So you're going to have 0 plus 24 minus 14. And then when they mean by V1 dot V1 is it's just what they mean by V1 dot V1 is it's just going to be 0 times 0 plus 4 times 4 plus 2 times 2. It's 0 times 0. This is V. This is V. and this is x. So when they mean by v1 dot v1 from down here, is it 0 times 0 plus 4 times 4 plus 2 times 2, which is 16 plus 4. And then this is going to be equal to 5, 6, negative 7 minus 0, 2, 1. Now you get 0, 2, 1 from this result. If you, I think you do. Well, it's 5, 6, 7 minus 0, 2, 1, which equals to 5, 4, negative 8. All right, and then basically you're going to get the same number, 0, 4, 2. And then 5, 4, negative 8. We did some type of linear change where the x got changed but the v stayed the same. Okay. Now we have to do one more to deal with this. We're not even gonna really do orthogonality. I'm just gonna do least squares. So scratch that off with the intro to statistics. We're gonna do one more part of this. All right, we gotta do one more problem. So that was just one type of this. This is the Gram-Schmidt. This is called the Gram-Schmidt process. All right. When I took physics, I mean, I didn't even get the opportunity to actually use matrices, which I think is neat to show. Okay. For some reason, they don't want to show them in a community college, which I think is absurd. They make the math easier, and they really make a difference. All right, we're going to do one more problem. And it's not really long, believe it or not. It seems like it is, but it's not. Okay. So this one, you're going to have A is equal to, see the negative 10, 2, negative 6, 16, 2. 13, 1, 3, negative 16, 1. 7, negative 5, 13, negative 2, negative 5. Negative 11, 3, negative 3, 5, negative 7. Okay. All right. This is our last matrix problem. All right, so you have to follow this setup. This is the Gram-Schmidt process, believe it or not. We're still doing the Gram-Schmidt process. Okay. So we say that V1 is equal to X1. And then over here we can say that V2 is equal to X2 minus X1 dot V1 divided by V1 dot V1 times V1, which is equal to X1. This is X2, not X1. It's a good thing I made that a 1. I can fix that. Okay. V2 is equal to X2 minus X2 dot V1 divided by V1 dot V1 times V1, which is then equal to X2. I'll fix that. x2 minus negative 1 v1, which is equal to 3. So what they meant by, I'm not sure what they meant, but it's 3, 3, 3, 3, negative 3, 0, 3. So I think V1, so they use the column of the matrix. So I'm guessing when they did x2, well, they said V1 was equal to x1, right? So x1 had to have been this one, and then x2 dot v1 is just this column by this column divide. Oh, they did this column dot this column, right? This times this plus this times this plus this times this plus this times this plus this times this, and then they divide it by this times this plus this times this times this plus this times, oh no, this time times this plus this times this plus this times this plus this times this plus this times this. Okay, and then they got that. All right. And then you do the same thing with the next one. So you say that V3 is equal to x3 minus x3 dot v1 divided by v1 dot v1 times v3, a v1. That's a v1. v1, which is then equal to, well, it's not equal to anything. Oh, that's what sucks being tired. All right, I'm going to clean that up. So v3 is equal to x3 minus x3 dot v1 divided by v1 dot v1. Remember this is a dot. And then that's times v1 minus x3 dot v2 divided by v2 dot v2 times v3, which is equal to x3 minus negative 1/2 v1 minus negative 4/3 v2. And then this whole thing, because I ran out of space here, this is, we could say that v3 is equal to 60660. All right, and then there's one more I have to show you. So you're gonna have x4, oops, v4 is equal to x4 minus x4 dot v1 divided by v1 dot v1 minus x to the 4th dot v2 divided by v2 dot v2 times v2 minus x to the 4th dot v3 divided by v3 dot v3 times v3. All right, and then that becomes equal to x to the 4th. Well, it's x4. So x4 minus, not x to the 4th, x4 minus 1/2 v1 minus negative 1 v2 and then minus negative 1/3 V3. Wow, it's amazing how I could fit that all in there. V4 is equal to x4 minus x4 dot v1 over v1 dot v1 minus x4 dot v2 over v2 dot v2 times v2. Oh, we missed a v1 here. There's supposed to be a v1. Okay. V4 is equal to x4 minus x4 dot v1 over v1 dot v1 times v1 minus x4 dot v2 over v2 dot v2 times v2 minus x to the fourth dot v3 over v3 dot v3 times v3 is equal to x to the fourth minus 1/2 v1 minus negative 1 v2 minus negative 1/3 v3. So you could see the Gram-Schmidt process. If you notice here, this pattern is the same. The v1s, the v2s, the v3s. And then the x to the fourth is repeating, which shows you how it's a scalar. Like, ignoring the numbers here, I mean, we could see already how this acts as a scaling. All right, and then I didn't show you what v to the fourth was equal to. So this entire thing is equal to, or to clean this up, let me just do like I did over here. We'll say that v4 is equal to, and v4 is down here, by the way. It's equal to 0, 5, 0, 0, negative 5. Okay, now, all we have to do is make an orthogonal basis for column space of A. So we have to take this and make an orthogonal basis, which basically, if we take v1, where is v2? Did we get v2? This was v2. So this was equal to v2. Okay. So we take v2, v3, v4, put them all together. And by the way, we keep v1. We keep this first one. So if we want to make an orthogonal basis for A, we want to make this an orthogonal basis. Okay. And orthogonal means normal. So if anybody wants to know what orthogonal means, it's whenever you have something, if it's pointing this direction, it's got to be orthogonal, pointing this direction. 90 degrees is what we call orthogonal. You'll hear all about this in 2D kinematic equations. So we want to make an orthogonal basis for this. All we simply have to do is repeat the first one. So we got 10, 2, negative 6, 16, 2. And then 2, we want to do, I think, yeah, we're on v2. v2 is 3, 3, negative 3, 0, 3. And then we must do v3, right? Because we just did v2. And then v3 is 6, 0, 6, 6, 0. And then we got to do v4. Because we did v1, v2, v3, and v4. v4 is 0, 5, 0, 0, negative 5. Okay. This is an orthogonal basis set. Took this number, made it an orthogonal basis. And we wanted to do it for A. That's what this was for A. So all of this was for A. All right. That is it for vectors, or for matrices. Okay. I think we can get rolling now. All right. Yeah. And like I said, this is probably going to be 2 hours long, but we'll see how long it gets. Okay, so what I'm next down to is a story. I want to do that before we even talk about energy. So, you have to understand with energy is it's a scalar. That's why I was showing you the dot product. Energy is a scalar just like time. Time is also a scalar, mass is a scalar, energy is another scalar. So there's 3 scalars that we understand. And the third one that we just found out is energy. So with forces, force is when I have to move something. It has to have some kind of direction to travel. Now what's nice with energy is we don't care about the direction. And what I was trying to show you earlier is that when we did forces, we didn't care about external forces, internal forces. But when we did look at forces, we were actually looking at external forces. I don't really like to use the word external, but that's what we did with forces. Energy's different. We want to care what's inside of the system. So we want to know not what's outside. In forces, we only care about what's surrounding the system. With energy, we want to know what's inside the system. So instead of just looking at external forces, we look at internal forces. So the way energy works is whenever I put work into a system, right? Let's say if I move an object like this pen or something. Let's say if I want to move an object, right? It could be anything. I'm moving to a coin. So let me say I'm going to move this quarter, right? I'm trying to find a nice looking quarter here. All right, let's say if I want to move this quarter. I'm going to move this coin, right? Well, if I move the coin, then I have to do some kind of work to the system, right? I can't just get it to move without doing work in the system. So I'm going to put work into the system to get this coin to move. But it takes a lot of force and a lot of work. And whenever there's work, wherever there's force, there's work. Whenever there's work, there's energy. Now, energy can't be created nor destroyed, but it can change forms. And here's the interesting part with energy. You can actually change the amount of energy that goes into a system. You can manipulate energy. You have the ability and power to change energy. And that's the nice thing with energy. It can't be created nor destroyed, but it can be distorted. It can be shape-shifted. It can be controlled. It can be harnessed. It could be like intensified or like down to a crawl, but we can't create it nor destroy it. It's very interesting. Now, energy is a very interesting concept. It's a lot like God. It's the deepest. This is the deepest topic throughout the entire season, which deserves 2 hours of talk. I mean, 2 hours of explanation, because energy is the deepest concept we're going to be getting into in this entire season. In this series, it is the deepest topic. Nothing gets as deep as this. Once we get into linear momentum, we're going to kind of just get out of the well. But energy is like the deepest part of the well. It's like when you reach the farthest part of a well. So like, imagine like a well, right? Or some kind of a hole, right? Some kind of a hole. Imagine that there's some kind of hole like this. When we did kinematic equations, we were kind of just at the surface here. Forces, we kind of went here. Energy, we're like all the way down here. So like this would be like kinematic equations would be around here. You could say these are kinematic, right? Kinematic. And then 3D velocity would be right here probably. 3D relative velocity. I didn't even spell velocity right. Hold on. Velocity. And then if you go deeper, you got Newton's laws, right? Newton's. And then, of course, we had space-time, right? Space-time. Newton's laws. Well, energy is all the way down here. Energy is all the way down to the very bottom of the well. That's why energy is so deep. It is the deepest topic in this entire season. I mean, nothing goes deeper than that. It's like in penetrating the center, the core of the earth. It is like hitting the center. Like, you can't go any deeper than this. And that's what's really cool. I mean, this is like the deepest. Now, we'll start climbing once, because linear momentum is kind of like right here. You got linear momentum And then you have rotation. And gravitation, I guess, is like the same level. Gravitation. But like, we go back to the surface again, but when we get to energy, it is the deepest topic in this entire season, which deserves 2 hours to talk, like, to explain. It is the closest to God that we ever get to. It's actually how we define God, as we think he's an energy. And when I think of energy, I honestly think it's like a flux. I honestly think that's a good way to understand energy. It's some kind of flow. And flux is actually this symbol. They call this phi. It's like an eye with a circle. That is flux. So that's what I think of energy. I think energy is some kind of flux. It's interesting. And what I wanted to talk about is where there's energy. It reminds me of this movie called The Matrix. So one way to think about it, if you ever saw the third one, like the very last one, they had a third one of the trilogy, and they talk about the architect. The architect's job was to balance an equation. His job was to balance it. The oracle's job was to unbalance the equation. It was the opposite. So she wanted to like kind of just trip the system up and kind of shake it up a little bit and kind of wake it up. Kind of get it like to move in a weird, any random direction possible. And it's interesting because energy kind of acts like that. Energy always wants to be balanced. Doesn't like to be imbalanced. So the way conservation of energy works is if you try to unbalance it, it's going to try every way possible to rebalance itself. Energy is like an endless battle between the balance and the unbalance. It's very interesting. And think of it like that. It's like a scale that's being like tripped or it's being tipped over. It's going to want to fight its way to get back to its balance again. And that's energy. Energy it acts in a very strange way like that. Nature does not like to be imbalanced. Like, it'll fight its way to balance, and it goes endlessly with this. It's like it's a never-ending battle between balance and the unbalance, and, and the justified and the unjustified. It's very interesting the way it is, and that's energy. It wants to balance itself no matter what. And I just thought that would be cool to share an explanation about. And it's like the movie The Matrix. And like I was thinking of The Matrix is that what if we're in some kind of program? Like what if we are in a linear program? Like what if everything is just linear? Like and it's kind of neat to think like that, because if it is linear, then everything is determined. But what we don't know is undetermined. What if we're in a simulation and we don't know exactly? What if we're programmed not to know the outcome? What if we already know the outcome, but we're not programmed to know it? See, I'm starting to think like that. And Zen Buddhists think like that too, and it's interesting. But my favorite character from The Matrix, I think, was the French guy, because he always thought things were like a causality and everything, and he talks about, he's got interesting words. Wherever he sees choice, he sees chaos or something. It's just interesting. Anyway. He believes everything's a causality. He had other words that were mentioned in the third one. I can't remember off the top of my head. But it's interesting stuff. And like I said, this deserves a little explanation. Okay. So I'm going to jump right to the summary. But we are not done. We got another chapter. Like I said, this is a long episode that deserves explanation. I mean, this is deeper than just doing forces here. I mean, it's so deep that it's over an hour. Okay. I think we did circular motion. I'm going to show you, I'm going to explain everything for energy. All right. So one way to think about work. Work is equal to force dot displacement. S is just fancy for displacement, which is equal to Fs cos theta. And remember I showed you the cos theta is the angle between two vectors? This is the angle between two vectors, and this is the dot product. So that's what this reinterprets to. The Fs cos theta is expressed in the angle between two vectors, and F dot S, it's represented as the commutative dot product. Commutative property. It's okay to say that multiplication is commutative because that, like when I pulled matrices, you cannot say that, but because we're talking about force, physics, we can deal with that. And phi is the angle, oh, you don't use theta, you use phi. And then phi is the angle between two vectors. Is angle between two vectors. So it's in a nutshell, it's really just this everything with energy is really just 2D. It's 2D. It's not 3D, 4D, 1D, it's just 2D. Other than that, I don't know if I should really do it diagrams here, but it's really the same thing as forces. So if you have a parallel force, or we call this a perp force, which perp is short for perpendicular, and then we'll call this a parallel force. And these are components, so they don't need to be vectors. And then between them is the force. And work is equal to Fs cos theta. And then the angle between, we'll call this phi. And then we say that work is equal to F perp S, or F parallel S. See, the dot product only cares about what happens over here to what happens all the way over here. That's what they mean by parallel. It's not perpendicular, because if it was perpendicular, the angle would turn from here, but then it would stop right here. We care about what is parallel. So parallel is when it starts from here, from zero, and then turns 180 degrees, which is half a circle. Half a circle is parallel, and it's parallel because if I flip this, it's still pointing in the same but opposite direction. Do you see it? You see that? So it's still, if it's turning this way, you can think of it like this. So if I have a pen, right, and I'm turning it this way, this tip isn't going anywhere. It's still pointing in the same spot. So that's kind of what they're talking about here. Other than that, it's just sliding blocks. So if you want to talk about kinetic energy, oh, I didn't mention about that. So kinetic energy is energy in motion. It's kind of like chasing a dragon. Kinetic energy, it wants to keep moving no matter what. And it's actually the easiest thing to solve. Potential energy is hard. So K is equal to 1/2 mv squared. That's kinetic energy. And then we say that work, I think it's work non-conservative work, or work total, is equal to K2 minus K1, which is equal to the change of K. And then if you want to express it in integrals, and area equals work done by force during displacement. You could also, and this is if you get a varying change, you would say that work is equal to the line integral from x1 to x2 times f sub x dx. And then work is equal to the line integral from P1 to P2 of f cos phi dl. Is it phi? Yeah. Which is then equal to the line integral from P1 to P2. And then you have f parallel dl. Okay. This is phi, by the way. It's not a don't symbol, it's a phi. Cos phi. All right, and then the last one, and then we say that this is equal to the integral of P1 to P2 of force dot d length. Now, this is a nice integral because what happens is the dot product cancels out the integral. You're going to see this when you get into Gauss's law. And now, if we want to talk about power. So power is like the work that's done to turn something on or turn it off. So power is just like time. It's not much different than time. Power is equal to the average, or what? Let's spell it out. So power average is equal to change of work over the change of time. And then if you have average power. If you have instantaneous power, we just call that power. That's equal to the limit as the change of time approaches 0 of the change of work over the change of time which is then equal to dw dt, a derivative of work with a derivative of work with a time derivative. And then power is equal to force dot. We could also say that power, this whole thing is then equal to force dot v. Force dot velocity. All right. So it's a derivative of work with a time derivative. Power is equal to force dot velocity. Okay. That is it for that part. We do have one more chapter called problems. Like I said, this is a long episode. Probably going to get this down to maybe, well, it's probably going to take more than 20 minutes, but it's not going to take more than 20 minutes. I mean, it's going to take more than 10 minutes. All right, there are a couple of examples that are good in this book that I wanted to explain. Couple of great ones, by the way. Now, the first one is conceptual. First one is going to be conceptual, and I think both of these are. These are conceptual examples. These aren't number crunching problems, which is a good balance because when we did matrices, I mean, we did number crunching. Okay. So, conservative or non-conservative? In a region of space, the force on an electron is F is equal to Cx j hat, where C is a positive constant. So the equation for this example is you're going to have force is equal to Cx j hat, where C is a positive constant. The electron moves around a square loop in the xy plane. Calculate the work done on the electron by the force during a counterclockwise trip around the square. Is this force conservative or non-conservative? The force is not constant, and in general it is not in the same direction as a displacement. To calculate the work done by force, we'll use the general expression for work. So we have to say that work is equal to the line integral from P1 to P2 of F dot force dot d length. And length is a vector, by the way. Where d length is an infinitesimal displacement. We'll calculate the work done on each leg of the square separately and add the results to find the work done on the round trip. If this round trip work is 0, force is conservative and can be represented by a potential energy function. The first leg from 0, 0 to L0 Okay, what's going to happen is, let me explain graphically what's going on with this problem. So you're going to have like a box. You're going to have some kind of a flat box that's in 2D dimensions. And then it's going to have arrows. So this one's going to go this way. This one's going to come down. This one's going to go this way. And then it's going to go up. It's going to go in like a square motion. Think of this as square motion. So this is when the force is equal to 0, and then we call this leg 1. This is leg 4. And then you're going to get coordinates too. So you're going to call this 0, 0. And then this corner here is going to be 0L, 0L. And then this one is going to be LL. And then down here, it's going to be L0. You can think L as 1. So it's 0, 0, 0, 1, 1, 1, 1, 0. You can think of it like that. Okay. And then call this leg 1. And then we say that DL See, this almost looks like circular motion. The only difference is we're expressing it with, and then you're going to see like vectors that increase. We call this the force. That's what that is. That's the force. And then the force here just kind of goes right here. And then DL must also go up here. And then the force here is equal to CL j hat. All right, and that's unit vector. And then this is leg 2. All right, and then we're almost done with the diagram. This is leg 3. And then DL is this one. And then you're going to have this, which is the force. So this is the force. Oh, sorry about that. Camera's very sensitive too, by the way. one little trip, I mean, it sends it off. Okay, so that was the force. The force are these arrows that climb up. Don't worry about this one. I couldn't really write it on the page. I couldn't fit it. But this is your force. Your force ascends. You notice when it's going in the direction the force diminishes, force is 0, force increases, and then force is just equal to the vector. And by the way, force is right here too. Maybe there is no force here. That's fine. It's just a line. Okay, that's basically what they were showing. On the first leg from 0, 0 to L0, the force is everywhere perpendicular to the displacement. So force dot d length is equal to 0, and the work done on the first leg is W1 is equal to 0. The force has the same value as equal to CLJ hat everywhere on the second leg from L0 to LL. The displacement on this leg is in the plus y direction. So d length is equal to dyj hat and F dot d length is equal to CLJ hat dot dyj hat, which is then equal to CLdy. Okay. The work on the second leg is then work 2 is equal to L0 to LL F dot d length, or force dot d length, which is then equal to line integral from y is equal to 0 to y is equal to L. And you can think of that as a change of variables of CLdy, which is equal to CL times the integral from 0 to L dy is equal to CL squared. On the third leg from LL to 0L, force is again perpendicular to the displacement, and so W3 is equal to 0. The net force is 0 on the final leg. From 0L to 0, 0, so work 4 is equal to 0. The work done by force, so W4 is equal to 0. The work done by the force on the round trip is therefore. So this is if you don't want to look at the calculus, you could just say that work is equal to work 1 plus work 2 plus work 3 plus work 4, which is equal to 0 plus CL squared plus 0 plus 0, which is just equal to CL squared, so you get the same thing. Okay. Because work is positive, the mechanical energy increases as the electron goes around the loop. This is not a mathematical curiosity, it's a much simplified description of what happens in an electric generating plant. In an electrical generating plant. There, a loop of wires move through a magnetic field which gives rise to a non-conservative force similar to the one here. Electrons in the wire gain energy as they move around the loop, and this energy is carried via transmission lines to the consumer. If the electron went clockwise around the loop, force would be unaffected, but the direction of each infinitesimal displacement d length would be reversed. Thus, the sign of work would also reverse, and the work for a clockwise round trip would be work is equal to negative CL squared. This is a different behavior than the non-conservative friction force. The work done by friction on a body that slides in any direction over a stationary surface is always negative. Alright, there is one more example. It's not as bad as that one. It's actually shorter. Alright, there is one more I want to show you first before we get to the summary. This one's not as bad. An electric force and its potential energy. An electrically charged particle is held at rest at the point x is equal to 0. A second particle with equal charge is free to move along the positive x-axis. The potential energy of the system is U of x is equal to C over x. So what they're saying is that the U of x is, sorry, I'm just tired. U of x is equal to the C over x. Okay. Where C is a positive constant that depends on the magnitude of the charges, derive an expression for the x component of the force acting on the movable particle as a function of its position. Solution identify and set up. We are given the potential energy function, U of x. We will define the corresponding force function using equation 7.16, which we just say that force sub x, or F sub x, is equal to, I didn't write that correctly. We got to put in an Euler notation. So F sub x of x is equal to negative du of x over dx. And you can see there's an interpretation between this equation and this equation. The derivative of 1 over x with respect to x is negative 1 over x squared. So for x greater than 0, the force on the movable charge particle x greater than 0 is F sub x of x. And this is funny because it acts the same thing as a partial derivative, but it's just direct. F sub x of x is equal to negative du of x dx. Which is equal to negative c of negative 1 over x squared. Which is equal to c over x squared. The component of the force is positive, corresponding to a repulsion between like electric charges. Both the potential energy and the force are very large when the particles are close together, small x, and both get smaller as the particles move farther apart, large x. The force pushes the movable particle toward positive values of x where the potential energy is lower. Okay. I just wanted to show you those because they were particle problems. Okay, so if you have gravitational potential energy and elastic potential energy. Now we're going to go to a summary. We're about to wrap this up. So work, gravity, gravitational work is equal to mgy1 minus mgy2. Which is then equal to u grav 1 minus u grav 2. U gravity 1 minus U gravity 2. All right. It's really hard. You know what? I have to put this over here or something. Okay, and then elastic work is equal to 1/2 kx1 squared minus 1/2 kx2 squared, which is equal to U elastic 1 minus U elastic 2, which is equal to the change, I think it's the negative change of U elastic. All right. This is gravitational work and elastic work. You get these results. Oh, I missed something with gravitational. So gravitational should be the same thing. You should have negative change of U gravity. Same thing with elastic. Okay. And then when you want to know total mechanical energy is conserved, you would just simply say K sub 1 plus U sub 1 is equal to K sub 2 plus U sub 2. Kinetic 1 plus potential 1 is equal to kinetic 2 plus potential 2. And then the total mechanical energy, if it's not conserved, so this is if it's conserved. This is conserved. Conserved energy. That's if it's conserved. Now, if it's not conserved, so if it's not, which you could say it's non-conservative. It's non-conservative energy, right? Non-conservative energy. If it's non-conservative energy, then you would have to say that K sub 1 plus U sub 1, K sub 1 plus U sub 1, so kinetic 1 plus potential 1 plus other work is equal to kinetic 2 plus potential 2. The only extra step is you have other work. You're adding other work because the other work is what makes it non-conservative. Okay, so anything that's conservative energy, you always get this back. Anything that's non-conservative, you don't. Now, conservative versus non-conservative, it's like when you have a wiggly path. Conservative is only going to care about the endpoints, so they're going to do what's called a linear fit. So they just care about the terminal points, like the initial and terminal or initial and final. Non-conservative cares about this, what happens in between. So non-conservative cares about all this. Conservative just cares about the linear trend. Cares about what comes in is equal to what comes out. It's kind of like network flow when we did that in the last, in forces and stuff. It's more like, you can think of that as more like conservative energy. Determining force from potential energy. So this is interesting. So F sub x of x is equal to negative du of x dx. And then you could say that F sub x, and now we're going to do partial derivatives. f sub x is equal to the negative partial of u with respect to x. And then f sub y is equal to the negative partial of u with respect to y. And then f sub z is equal to the negative partial of u with respect to z. Okay. That's all three of them. Now, if you wanted to take the gradient is called a directional derivative. So the gradient is an operation. So if you want to take the gradient, right? And we call this gradient a direction. If we take the gradient of the force, now let me explain this. So if we wanted to take this gradient, right? Which this is called nabla. This is known as nabla, which comes from the Phoenicians' harp, because it's shaped like a harp. So if we wanted to take this as a gradient, which is nabla force, this becomes equal to the negative partial of u with partial of x I hat plus partial of u partial of y j hat plus the partial of u partial of z k hat. But we care about the force, so we interpret this as the force is equal to the negative partial of u, partial of x, I hat plus the partial of u, partial of y, j hat plus the partial of u, partial of z, k hat. And one way to think about this is all of these are negative, so all we did was factor out the negative and you're going to get a straight up addition. This is why I've been like harping, funny right, harping and talking about a Phoenician harp. Why we have to talk about addition, we can't think of subtraction, we have to think of addition. A lot of that's important, and the angle between two vectors and commutative, non-commutative, all that stuff. It builds up from that. So, sorry about the chair creaking. I was just trying to I couldn't really take notes very well because the book was on the other side. But other than that, this has been a great episode. This is probably going to be the longest one. Rotation, I'm either going to make that one episode or I'm going to make it two. I'm thinking I'm just going to do a part one and a part two. Linear momentum is next week. If you notice, a lot of this stuff that I showed you, it looks linear. This is like a linear equation. So if you look carefully, this is a linear equation. If you look at the conservative energy and non-conservative energy, they look like linear equations. So just keep an eye out on that. This is linear. This is also linear. Nothing that we have done is nonlinear. And if you look at this example, this is a linear equation, except for this part. But if we really look at the theorems and the definitions and definitions, this is the conserved energy is linear. Non-conservative energy is also linear. So keep an eye on that for the next episode. Trying to see if there was another summary we covered too, wasn't there? I'm trying to find the page. It's here somewhere. I think this was the page. If you look at the total work here, this also looks like a linear equation, right? This total work looks just like a linear equation. There wasn't much linear with that page, but if you look at conserved energy and non-conservative energy, they're linear equations because they don't have any exponents. The next unit we're going to cover, which is next week, we really are supposed to combine this, but I'm not going to do that. It's going to be on linear momentum, and I got some surprising stuff to share about. But other than that, it's the same thing that we're doing now, but it's more on vectors. So linear momentum gives us a position. Energy doesn't really have a position to worry about because it's a scaling function. It's a scalar. So whenever we have a system, we only care what's the scalar. Now, a scalar is any integer that can add up. It can be a positive number, a negative number, or zero. I feel like I should show you an example of a scalar, like a better one. So imagine you're going to have 3 points. Let me do a scaling really quick before I close this up. So imagine you're going to have 3 points, right? I mean, we could do points or whatever you want to do. Vectors, we'll do points. So let's say we have 3, 3, 9. And then we want to know what is the dot of 3, 3, 9. Let's do 4, 4, 6. So how I would do the scaling is I have to do 3 times 9 plus 3 times 4 plus 9 times 6, right? And then if you simplify these numbers, you're going to get a scaling. I have to get a calculator. I swore I had one earlier. So 3 times 9 is 27. You're going to get 27 plus 12, right? 3 times 4 is 12. And then I think 6 is 54. And then if you do 27 plus 12 plus 54, you're going to get 93. So this becomes equal to 93. This is what you know as a scalar. It's a value. So whenever you have vectors, like let's say we call this I hat, J hat, K hat, right? Or I hat, J hat, K hat. The proof is this. So if I do I hat times I hat plus J hat times J hat plus K hat times K hat. Now what happens when you multiply these is you have a scaling in between, right? This is going to cancel. This is going to cancel, and this is going to cancel. It's the vector world. When we multiply with a scaling, the vectors, they cancel out. It's like a stalemate. So that is the scaling concept. I just wanted to show you really quick. If you ever had an orthogonality, which is, it could be 3 vectors or more, you'd have like something squared plus, I don't know. You're going to get some approximation of some integer. But other than that, that was something else that I saw in chapter 6 and I was surprised I didn't see in the homework problem. I guess because we did the Gram-Schmidt process. But this has been a very interesting episode. The next one's not going to be as long at all because I won't even have to show you vectors when we get into linear momentum. I do have to show you systems of linear equations. I'm going to explain the tenzan, which means strike off in Japanese, and we'll talk about that. Other than that, I mean, that'll be the next episode is linear momentum. It won't be as long as this one. It'll be quicker. It's not as much difficult to explain. I think there's also going to be center of mass, but it's not going to be like this video. Alright, this has been a great video. Stay tuned for the next one. Thanks.